Many natural gas reserves contain nitrogen in concentrations ranging to about 20%. To meet pipeline specifications, the nitrogen level must be reduced to below 4%. Large majority of nitrogen removal facilities use cryogenic distillations, but such units are economical only for large capacity wells. For smaller reserves, pressure swing adsorption technology has economic benefits, especially because the feed mixtures are available at high pressures. It is desirable to use adsorbents and PSA technologies that are selective to nitrogen. However, for most known adsorbents, the adsorption selectivity for nitrogen-methane mixtures is in favor of methane due to its higher polarizability. One practical solution is to rely on diffusion selectivities by using microporous materials such as LTA-4A zeolite. The suitability of LTA-4A zeolite for kinetic separations of nitrogen-methane mixtures was first suggested by Harry Hapgood in 1958. And the objective of this presentation is to examine the potential of LTA-4A zeolite for nitrogen removal from natural gas streams. Hapgood in 1958 published a set of experimental data on transient uptake of nitrogen and methane in LTA-4A zeolite at a temperature of 194 Kelvin. The data is remarkable in that it shows that the nitrogen uptake shows an overshoot in the molar loading, and the value of the peak is about 2.2 moles per kilogram, significantly higher than the value at equilibrium, which is 1.2 moles per kilogram. The uptake of methane, on the other hand, is monotonic, and the component loadings approach its equilibrium value in a monotonic manner. The attainment of supra-equilibrium loadings of nitrogen and transient overshoots are signatures of kinetic separations. Before we delve into the details of the Maxwell-Stefan modeling of intracrystalline diffusion, let us gain a qualitative understanding of the motion of molecules within the cage window structure of 4A. Towards this end, I will play video animations prepared from MD simulations. There are many things to look at in the animations. Firstly, note that the blue-colored guest molecules are nitrogen. The green-colored spheres are the sodium cations, and the cyan-colored spheres are the methane molecules. You will also note when you observe the simulations that the green-colored spheres, that is the cations, act like goalkeepers in a soccer match, trying to prevent the intercage hopping of guest molecules. Another thing to note when I play the simulations is that nitrogen jumps lengthwise across the windows from one cage to the adjacent cage, and that happens in this window region. So if you want to have a look at nitrogen hopping, look at this window. If you want to see the goalkeeper sodium cations in action, look at this window. And for the duration of this animation, the methane molecule is unable to cross the window because the animation is only run for a short period of time. Let us have a look. Here's the goalkeeper. Here's the nitrogen molecule attempting to cross the window, and it has just managed to cross it. Play it again. We set ourselves the objective of modeling the transient uptake experiments of Hapgood. In particular, we'd like to investigate the physics behind the transient overshoots in the nitrogen loading as reported in the Hapgood experiments. To meet these objectives, we adopt the Maxwell-Stefan diffusion equations. For background reading on the Maxwell-Stefan diffusion equations, you may consult these publications of mine. There are also other YouTube presentations on my channel that provide the background to the Maxwell-Stefan equations. Briefly, the Maxwell-Stefan equations recognize that the fundamentally correct driving forces for intracrystalline diffusion are the gradients in the chemical potentials. For a binary mixture, the Maxwell-Stefan equations can be written in this manner, in which the chemical potential gradients are related to the fluxes N1 and N2 of components 1 and 2. We define three types of Maxwell-Stefan diffusivities. D1 and D2 reflect the molecule wall interactions, and there's another diffusivity D12 that quantifies correlations in molecular jumps within the microporous material. For LTA-4A zeolite, the interk jumping of gas molecules are practically uncorrelated, and these terms, the first right members, can be ignored. The chemical potential gradients, in turn, can be written in terms of the gradients of the molar loadings Q1 and Q2 that are accessible from experimental measurements by defining a matrix of thermodynamic correction factors. For a binary mixture, we have a two-dimensional matrix with 4 elements: gamma 11, gamma 12, gamma 21, and gamma 22. The elements of this matrix can be calculated from the molar loadings Qi and the partial fugacities Fi and Fj of the component species in the bulk fluid mixture. The matrix of thermodynamic correction factors can be determined from an expression that describes the mixture adsorption equilibrium, for example, the ideal adsorbed solution theory. Let's model the nitrogen methane mixture uptake in LTA-4A zeolite using the Maxwell-Stefan diffusion equations. The D12 term signifying correlations between 1 and 2 need not be accounted for because the guest molecules jump one at a time across the windows from one cage to the adjacent cage of LTA-4A zeolite. We take the diffusivity values based on the data provided by Habgood, and let's first consider the transient uptake simulations in which the thermodynamic coupling effects are duly accounted for. The uptake of nitrogen is plotted is followed here as it develops inside the crystallite of 4A zeolite. This is the surface of the zeolite, which is in equilibrium with the bulk gas mixture. This is the center of the crystallite. The nitrogen shown by loadings in moles per kilogram shown by these red lines. Note that this is the loading at the surface, and the peak loading is significantly higher, and it diffuses much faster than methane. And at this time, the maximum loading has been achieved, and the loading inside the crystal of nitrogen decreases finally to reach the value at equilibrium. So it undergoes overshoots as observed in the experiments. Let's now perform the same set of simulations, but now ignoring thermodynamic coupling and assuming that the matrix of thermodynamic correction factors is the identity matrix. In other words, gamma ij is the Kronecker delta. These simulations are shown here. Again, this is the surface of the crystallite. This is the center. The red line is for nitrogen. The blue lines are for methane. Nitrogen penetrates faster into these central regions, but you will note that no overshoot has been experienced so far by nitrogen. Methane is tardier in its uptake and takes a significantly longer time to reach equilibrium. But determining the spatial average of the component loadings as presented in the foregoing slide, we can determine the spatially averaged component uptakes for components 1 and 2, nitrogen and methane. The experimental data of Habgood, shown by the blue circles for nitrogen and blue triangles for methane, are compared with the spatially averaged component uptakes from the simulation data. The continuous solid lines are the simulation results in which the thermodynamic correction factors are duly accounted for. The dashed lines are the corresponding simulation results in which the thermodynamic correction factors are ignored, and the matrix of thermodynamic factors is taken to be the identity matrix. We note that there is good agreement between the experimental data of Habgood and the simulations in which gamma ij is properly accounted for. On the other hand, if gamma ij is taken to be the Kronecker delta, in other words, the thermodynamic correction factor matrix is taken to be the identity matrix, no transient overshoot for nitrogen is anticipated, as shown by the dashed red lines here. And there is poor agreement, qualitative and quantitative, with the experimental data of Hapgood. We therefore conclude that the Hapgood experiments with transient overshoots can be described only by a model that takes due account of thermodynamic coupling effects. Indeed, the transient overshoot of the more mobile guest is a signature of kinetic separations. There is another way in which we can plot this data, and that is in composition space. We plot the nitrogen uptake versus the methane uptake. These are the component uptakes at time t0 at the start of the experiment. And this point here is t is infinity, is when equilibrium is reached. The red circles represent the Hapgood data plotted in composition space. The red line shows the trajectory from time t0 to time t is infinity, the trajectory that is followed by in the simulations in which thermodynamic coupling effects are duly accounted for. And this is in good agreement with the Hapgood experiments. On the other hand, if thermodynamic coupling effects are ignored, the equilibration trajectory follows a monotonic path to equilibrium in quantitative and qualitative disagreement with the Hapgood experiments. So a signature of kinetic separations is that in composition space, the equilibration trajectory follows a scenic route. Let us examine the concept of the kinetic selectivity for binary mixtures. The kinetic selectivity is defined as the ratio of the spatially averaged component loadings for 1 and 2 divided by the corresponding ratio of the partial pressures in the bulk gas phase surrounding the particle. For the Hapgood experiments, the transient uptake selectivity determined from this formula are plotted here as a function of the Fourier number. For comparison, the green line shows the kinetic selectivity that is calculated using a formula that is often used in the published literature as being the ratio of the Langmuir constants for components 1 and 2 multiplied by the square root of the ratio of the diffusivities for components 1 and 2. They're shown here. The experimental data for Hapgood lie about a factor 2 above the value calculated from this formula. The continuous red line are the calculations of the kinetic selectivity from the simulations presented in the foregoing slide, in which thermodynamic coupling effects are duly accounted for. The blue line is the kinetic selectivity calculated from the simulations in which thermodynamic coupling effects are ignored. Looking at this data, we note that the formula that is widely used in the published literature is a limiting case of a model in which thermodynamic coupling effects are ignored. Put another way, the commonly used formula is based on a model that is not in quantitative agreement with the Hapgood experiments. Also shown on this graph by the dashed line is the adsorption selectivity, that is the ratio of the Langmuir constants. What we conclude from this comparison is that the simplified formula that is often used in practice must be viewed as being an approximate measure of the kinetic selectivity, whereas by taking due account of thermodynamic corrections, we may obtain selectivities exceeding that determined from the simple formula. So far, we have been examining transient uptake within a single particle. Let us turn our attention to breakthroughs in a fixed bed adsorber in which a feed mixture is introduced at the inlet, and we look at the gas compositions at the exit. The results of the simulations of breakthroughs for 2080 mixtures of nitrogen and methane at a total pressure of 100 kilopascals are shown here for a temperature of 194 Kelvin, corresponding to the temperature used in the Hapgood uptake experiments. The blue line is the breakthrough of methane that occurs earlier, and the red line shows the breakthrough for nitrogen. This is the dimensionless concentration at the exit, and the x-axis is a parameter in which T is the time in seconds, Q naught is the volumetric flow rate at the inlet in liters per second, divided by the mass of the adsorbent in kilograms. We note here, since the methane exits the fixed bed earlier than nitrogen, it is possible to recover purified methane meeting pipeline specifications. So kinetic separations with LTA-4A zeolite are feasible at 194 Kelvin. Let's move to the right-hand side, which shows breakthrough simulations for the same feed mixture composition, but the bed now operates at a temperature of 295 Kelvin. These simulations are based on the isotherm fits, which I have shown in a previous slide, along with the diffusivity data reported by both Wilkins and Hapgood. At the higher temperature, we note that nitrogen breaks through earlier, and no kinetic separation is possible at this temperature. Indeed, LTA-4A zeolite is able to produce purified methane only at cryogenic temperatures, and this is also the claim made in the patent that was awarded to Hapgood. Let us summarize what we have learned from our analysis of nitrogen methane mixture separations in LTA-4A zeolite. On the basis of the analysis of the Hapgood experiments, we have established that transient overshoots and serpentine equilibration trajectories in composition space are signatures of kinetic separations of nitrogen methane mixtures in 4A zeolite. On the basis of breakthroughs in fixed bed adsorbers, we've also established that kinetic separations with LTA-4A are only possible at cryogenic temperatures. As the temperatures are increased to above, say, 270 or 280 Kelvin, no kinetic separations are possible. And therefore, in practice, we have to resort to materials such as barium exchange ETS4. ETS stands for Engelhardt titano-silicate, with which kinetic separations are possible at higher temperatures. And in my presentation, Nitrogen Removal from Natural Gas, on my YouTube channel, the analysis of this material is presented that demonstrates the applicability of BA80 ETS4 for purification of natural gas.